Okay, this video is going to be awesome because we'll be talking about the three most important coordinate systems in a multivariable calculus class. They are the rectangular, cylindrical, and spherical coordinate systems. And we'll be talking about the convergence formulas between them. Let's focus on rectangular versus cylindrical first. And here, we are in the three-dimensional space now. Let's say we have a point here. How do we describe it? In the rectangular world, we just have to go left, right, forward, backwards, and up and down. So right here, we just have to go in the x direction and then go to the y direction. And then this is also going to be x, and then we just kind of like go up. That's the z direction. So for this point here, we just label that as x, y, z. Now, for the cylindrical situation, this is how we do it. For the base right here, that's the xy plane. On the xy plane, what we will do is, we will do the usual polar way. What I mean by that is, we are going to start with the past the x-axis, and then we are going to rotate, and then we are going to go directly to the under the point. So have a look. We will have to first rotate a certain angle, and then we will have to move forward until we can see that the point is right above us, or maybe below us. This rotation on the xy plane, we will call that theta, and this distance from the origin to under the point, we call that r. It's really just like the polar coordinate systems that we see in the two-dimensional situation. And then once we are, the point's right above us, we can just go up. In this case, that is still going to be z. We are going to write this point as r first though, and then theta, and then lastly we put down z. And why is this called the cylindrical coordinate system? Because when we do this rotation, you can imagine that, hey, we have a what? We have a bunch of circles. It's like a cylinder, cylindrical coordinate system, like so. Now, how do we convert from rectangular to cylindrical? Suppose we have x, y, and z given. Let's first talk about how to get the r. The r is the distance from here to here. And again, just like the polar way in the two-dimensional situation, r could be negative. And if you look at the base here, we have the x and also the y, then for a right triangle, so we can say by using the Pythagorean theorem, r squared equals x squared plus y squared. Done. Next, how do we get the angle here though? Again, this right here is the right triangle, y is the opposite, and then the x right here is the adjacent. So we can use tangent and say tangent theta equals opposite over adjacent. And lastly, the z, guess what? It's the same z, right? Because it's just go upward, so z equals z. Done. Now, suppose we're given cylindrical coordinate system, how do we get to the rectangular system? Here, we will have to project the x from here to here, right? So let's say this right here is the x distance. Let's focus on the x first. If you look at this right here, this is the hypotenuse of this triangle, just like what we did earlier. Hypotenuse and the x is the adjacent corresponding to the theta, so we can use cosine. So we can say cosine theta equals adjacent over hypotenuse. And then if you want to get x by itself, just multiply on both sides. So x equals r times cosine theta. Similarly, to get y, which is the opposite side of this triangle, it will be just sine. So you can say sine theta equals opposite over hypotenuse, and then multiplying r on both sides, we get y equals r times sine theta. And lastly, if you want z, use the same z, of course, z equals z. Now let's talk about rectangular versus spherical. And here we have a point in the space. How else can we describe it? Let me give you a live demo first. Let's say I have a fly over there, somewhere in my room. And what I have is a laser gun. I'm going to hold it up like this. And I'm facing this direction by default. The default direction is the positive x-axis. Now, I want to get to the fly. First, I will have to do a rotation. I will have to turn my body, right? So the first rotation is right here. And that is just like what we did earlier with the cylindrical coordinate system. It's the polar in the xy plane. Now, I can see the fly over there, but my laser gun is still pointing upward. So what do I have to do? I will have to do this, right? So I can aim the fly. So the second rotation is from the positive z-axis to here. And we are going to call that angle phi. And now, once I can aim the fly, I will just shoot from here to there so I can get rid of the fly. That distance from here to here, we call that rho. First, for this point, we're going to call that rho, theta, and then phi. And there are some conditions that we have to talk about for the angle. Let's talk about phi first, rho first. Rho, it has to be non-negative. Unlike the r that we had earlier, in the polar world and also the cylindrical coordinate system, the r could be negative. That's just you go backwards. But for rho, non-negative. And then the angle phi, we want it to be from 0 to pi radians, because we want to just go like this to there, from 0 to 180 degrees. So these are the conditions for this and that. The angle theta doesn't matter. You can turn, rotate however many ways that you want. Now, suppose we have a rectangular coordinate. How can we change that to spherical? First, let's talk about how we can go from the origin to this point, which is the rho that we want. Well, we can just use the 3D version of the Pythagorean theorem. But because we want the rho to be non-negative, we'll just take the positive square roots on both sides, and it's just the square root of x squared plus y squared plus z squared. It's also the distance formula in the three-dimensional space. Now, how can we get the angle theta? It's from here to here, right? Well, on the xy plane, we can just do the polar way. We can look at this triangle. Once I connect from here to here, opposite, adjacent. So use tangent. So we get y over x. Lastly, how do we get the angle phi? This one is a little bit trickier. To do so, we actually have to focus on this triangle. In fact, this is also a right triangle with the right angle here. Because once you have the point right here, this, right, it's just like the polar way you get to the bottom of this point. This point is right above us. So it's perpendicular. That's why it's 90 degrees. And let me just put on this triangle right here for you guys. First, we have the positive z-axis. And then we have the rho right here. And then we have the angle phi right here. And this right here is the z value right here. And then the bottom here is the blue part. I know it's r. I'll just put it down right here. Yeah. And here's the deal. Here and there, they are vertical. So they are parallel. That means this angle and that angle must be equal because alternative interior angles are equal. Now, by looking at this triangle, we have to figure out phi. Use cosine. Cosine of phi equals adjacent over hypotenuse. And now you might be wondering, why don't we use sine? Sure, we can also say that sine phi equals opposite, which is r, over hypotenuse, which is rho. We're actually going to use this one for the angle phi once we get to there, yeah? Because remember, we want the angle phi to be in between of 0 and pi. If you set it up right here like this, once you use inverse cosine, the range of inverse cosine does go from 0 to pi, which is very nice. So do not use sine or tangent. Right here, let's just go ahead and say cosine phi equals z over rho. And we know rho in terms of x, y, z, so I'll just put it down right here. Square root of x squared plus y squared plus z squared. Let's take a look at what if we have spherical coordinate. How can we get to rectangular? First, let's get the x value. So it's from here to here. Yeah, that's the x. And perhaps I'll just finish the picture. From here to here is the y. And this is also x, of course. And then we have to go up. And that is the z. Okay. X and y is a little bit trickier. First, we are going to connect from here to here. And this is r, which is this one right here. Now, to get x, well, you can just look at the xy plane. We know that x equals r times cosine theta, the usual conversion of the polar coordinate, right? And then, of course, we can also say y equals r times sine theta. But now, here's the trouble. Technically, we don't have r given. But it's okay, because we can look at this picture. We have what? We have phi and rho. For r, how can we figure it out? It's right here. Sine phi equals r over rho. So we can just multiply rho on both sides. So we can say r equals rho times sine phi. Then of course we can just put this to here and here. So x equals rho times sine phi times cosine theta, and then y equals rho times sine phi, and then times sine theta. Just like that. Now, lastly, how can we get z? Again, look at this triangle here. We have what and what given? We have phi given and rho given. We're trying to find z. And guess what? We have it right here as well, right? Z, we can just multiply rho on both sides. So that will give us rho times cosine of phi. Just like that. Now finally, cylindrical versus spherical. So suppose we have r theta z given. How can we get this, and that? First, to get rho, that's the distance from here to here. And to get rho, we can just look at this triangle, which is a right triangle, and I'll put it down right here. Here is the rho, and here is the z value, and then the base is the r. Notice this time we have r and z given, so we can just use the Pythagorean theorem and take the positive square root and say rho equals the positive square root of r squared plus z squared. Done. And in fact, this is how you can prove the 3D version of the Pythagorean theorem as well, because r squared equals x squared plus y squared. And that's how we got the expression that we had earlier. Next, here we have theta. Here we also have theta, so that's perfect. Theta just equal to theta. Yay. Finally, to get the angle phi, which is here, well, this right here is our z-axis. Then here is the angle phi, which is also going to be the same right here. And remember, the condition on phi is that it has to be in between of 0 and pi. So do not use opposite and adjacent. Rather, we should use adjacent and hypotenuse. So here, cosine phi equals z over rho. And rho, we know it's that. So we can just say cosine phi equals z over square root of r squared plus z squared. Now, if we have spherical, then let's see, rho, theta, and phi are given. First, we are going to figure out r, and r is the distance from here to here, and this is going to be, right here we have the z, yeah? So how can we figure out the r? And keep in mind though, this time rho is given. I'll put this down right here. So we have rho, and then this right here is the angle phi, and this angle is also angle phi, and then we have the r down here. So what can we use? Opposite and hypotenuse. So we can say sine of phi equals r over rho. So in another way, we can just multiply rho on both sides. We can say r equals rho times sine phi. And then theta, it's the same as that theta, so that's very nice. Lastly, ladies and gentlemen, how can we get z? Z is also right here already, right? And this time we can use what? Adjacent and hypotenuse. So we can say cosine phi equals z over p rho, and then we can just multiply the rho on both sides. So z equals rho times cosine v. Done.